Good morning, dear students. Welcome to physics session again. In our last physics session, we dealt with a device that is electric motor. Shall we? Did we study that? Yes, indeed. We studied about it, isn't it? Electric motor. What is the basic principle behind that? As we studied, when a current carrying conductor is placed in a magnetic field such that the direction of the current is perpendicular to the magnetic field, it experiences a mechanical force. Am I right? That is the basic principle behind the motor. Whatever this force that produced causes the conductor to move. Now, let us imagine a situation in which a conductor is moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. What may happen? Got it? What I told you? Imagine that a conductor is moving inside a magnetic field. A conductor is already moving inside a magnetic field, or a magnetic field is changing around a fixed conductor. What may happen? Here, a scientist, English physicist Michael Faraday gave the answer for this question. He conducted experiments regarding this in 1831, and through this Faraday made an important breakthrough in the physics field. Here you can see the image of Michael Faraday. He was an experimental physicist, children. Let me tell you something about Michael Faraday. He had no formal education like you. You are getting formal education in schools, isn't it? But he did not get formal education. He worked in a bookbinding shop during his early years. Bookbinding shop. He used to read books that come for binding. What an interest, see children. Interest at its best. You can observe here, whatever books came for binding works, he used to read them with interest. And in science, he got interest in this way. And Faraday made several path-breaking discoveries, including electromagnetic induction and other laws. By his interest, he can achieve this, children. So this must be an inspiration to all of us. Later, even though he did not get any formal education, several universities conferred on him the honorary degrees. But simply, he turned down such honors. What he need is, Faraday loved his science work more than any honor. So that is the speciality of Faraday, and that must be an inspiration to us, children. Now let us come to his discovery about the magnetic field and the force acting on the conductor. Okay. By conducting some experiments, he proved that a moving conductor in a magnetic field can produce electric current. Is it surprising, children? Yes, it must be, because whenever a moving conductor is in the magnetic field, it produces electric current. This was the breakthrough discovery done by Faraday. Let us know more about it. Children, as I told you, Faraday made an important achievement by discovering how a moving magnet can be used to generate electric current. See, children, for that, the principle to understand and to observe that effect, we can perform the following activity, and this activity was actually done by Faraday. For that, we need many turns of copper coil. You can observe there on the screen, and a galvanometer. You can observe, children, it is a box like there. It is a galvanometer and a magnet, bar magnet we need for this activity to perform. Now, here you can observe, children, the ends of the coil, that is copper coil, are connected to the galvanometer. What is a galvanometer? A galvanometer is an instrument that can detect the presence of a current in the circuit, and also when its pointer moves towards the particular direction, we can understand about the direction of the current also. Depending on the direction of the current, the pointer of the galvanometer deflects. When no current is flowing through the conductor, it will show 0 reading. Okay, shall we start the experiment? Here we have taken already, as I told you, the copper coil, the galvanometer and the bar magnet. When we are trying to insert the bar magnet. Here bar magnet is outside now. Observe, children, properly there. You can observe the copper coil, the galvanometer and the bar magnet. When we are trying to insert the bar magnet into the coil, you can observe that as the magnet is moved near the coil, there is a momentary deflection in the galvanometer. You can observe, children, there. Momentary deflection is observed in the galvanometer. And when we take it out in the opposite direction, we can observe the momentary deflection. When it is stationary inside the coil, you can observe, children, the pointer of the galvanometer shows a 0 reading. So here you can observe that what is happening here. The changing magnetic field. When there is changing magnetic field is there near the coil, that induces the current in the conductor. So the changing magnetic field induces the current in the conductor. This phenomenon is known as a electromagnetic induction, children. You can observe here, if you move the south pole of the magnet, as we observed here, when we move the south pole of the magnet here, children, towards the end, one end of the coil, the deflection in the galvanometer would be to one side. When we insert north pole north pole into the coil, the direction of the deflection of the galvanometer will be the opposite to the previous case. And also, when the coil and the magnet both are stationary, the galvanometer pointer shows 0 reading. That means that there is no current in the circuit. What we can understand by this activity, children? The motion of a magnet with respect to the coil produces an induced potential difference which sets up an induced electric current in the circuit. As you know, there must be potential difference across the two ends of the conductor so that it can set up the electric current in the circuit. Unless there is no potential difference developed, we cannot get current. So, whenever there is the relative motion between the magnet and the coil, I am telling here the magnet can be moved into the coil or coil can be brought near the magnet. Both cases are possible, children, here. So, whenever we move the magnet towards the coil, there is change in magnetic field. It creates the change in the magnetic field linked with the conductor, so that induces current. What we have to understand, when north pole of the magnet is inserted into the coil, the deflection, the momentary deflection, children, that is momentary deflection will be towards one side, as we observed in this activity. And when we try to insert south pole of the magnet into the coil, the deflection is towards the opposite side as before, to the previous one. It is opposite to that we observed. And also, when the coil and the magnet are stationary, both are stationary, there was no deflection in the galvanometer. So, no current produced. So, what we can mainly understand is, when the polarity changes, the current also reversed. The direction of the current also reversed. And also, when there is a stationary magnet and coils are there, no current was flowing in the circuit. But when there is relative motion between the magnet and the coil, the deflection is seen. That shows that current is flowing through the circuit. So, there must be relative motion between the conductor and the magnet. Then only it can set up the electric current in the circuit. This was the big breakthrough that was first observed by Michael Faraday experimentally. I hope you understood his experiment. Through this, what we can understand, what are the inferences also you understood, I hope. Children, we conducted the experiment. We conducted an activity done by Faraday, and we observed the effects of the experiment. In that, we used the magnet which is moved into the coil, and we have seen the deflection in the galvanometer. Let's now perform the variation of activity. This activity, whichever we have done previously, in which we are using a current carrying coil instead of the moving magnet. And the current in the coil can be varied. Can we do that? How we can do it? In the previous sections of this lesson, we studied that a current carrying conductor acts as a magnet temporarily. That means that as long as current is passing through the conductor or the coil, it acts as a magnet. Isn't it, children? So, using that basis, let us perform another activity in which we are using the instead of moving magnet, we are using a current carrying coil which can act as a magnet. Shall we start? Okay. Here is the arrangement. Observe, children. You can see the two coils. Observe here, children. Two coils of various turns. Here you can observe one coil is having more turns, another coil is less number of turns. That the coil whichever having more number of coils is known as coil 1. That is primary coil. That coil 1 is a primary coil, children. And whichever coil having less number of turns, that is a secondary coil. You can observe there, whichever having more number of coils, primary coil, less number of coils, that is the secondary coil. You can observe, children, here. And these two coils are taken together, and these two coils are inserted over a non-conducting cylindrical roll. We can use even paper roll also. Inside that they are these two coils, coil 1 and coil 2, which are known as primary coil and secondary coil, are inserted. Primary coil which one? That is having more number of turns. Secondary coil which one? Having less number of turns. We can say about, for example, 50 and 100 maybe. The primary coil having 100 turns, secondary coil may be 50 turns, like that. Okay. Coil 1, you can observe, children, here. Coil 1 is connected in series with a battery and a plug key. On the left side of the picture, on the screen, you can observe the having more number of turns. Whichever coil having more number of turns, that is coil 1 or primary coil, that is connected in series with a battery and a plug key. And the coil 2 is connected to simply a galvanometer, children. You can observe there, it is connected to a galvanometer. Okay. Now, let us start the experiment here. Now, the key is plugged now. You can observe, children, the key is plugged. Now, you can see the momentary deflection in the galvanometer. Current is flowing through. You can observe, children, current is flowing there from the positive terminal to negative terminal. You can observe. And you can observe, children, whenever the key is removed, the key is opened, there is also, during that, we can see the momentary deflection, but it is in the opposite direction. Again, you can observe, children, again it is plugged. The current is flowing. The momentary deflection can be seen in the galvanometer. Understood? So, what we can observe here, we will observe that the needle of the galvanometer instantly jumps to one side and just as quickly returns to 0. You can, in the previously, you can observe, children, here the momentary deflection. You can observe here momentary deflection. See here, children, you can observe momentary deflection as quickly as it will return to 0 whenever the key is plugged once and it is removed. I hope you are watching there in the video. You can observe momentarily deflection. That is, momentary deflection is seen in the galvanometer. Momentary deflection, and quickly it returns to 0. This observation is seen, children, in the galvanometer. What does it indicate? It indicates that a momentary current in coil 2 is induced. The galvanometer showing deflection means that there is a momentary current flowing through coil 2. And we observed both the ways, when the key is plugged and also when the key is opened. In both the cases, we have seen the momentary deflection in the galvanometer. This shows that the current is momentarily induced, but in the opposite direction. Children, always observe, when we plug the key, in one direction. The pointer of the galvanometer moved to one side and quickly returned to 0. When we opened the key, we have seen the deflection in the galvanometer, but it is to the opposite direction and quickly returns to 0. It means that the current is flowing in the opposite direction in coil 2 this time. As soon as the current in the coil 1 reaches either a steady value or 0, the galvanometer in coil 2 shows no deflection. Whenever steady value is there, no deflection is there, certainly there will not be any current. From this observation, we conclude that a potential difference is induced in the coil 2 whenever the electric current through the coil 1 is changing, that is starting or stopping. Coil 1, as I told you, primary coil, coil 2, secondary coil, isn't it, children? Hence, the change in magnetic field lines associated with the secondary coil is the cause of induced electric current in it. Observe, children, that only the basis of electromagnetic induction. The change in the magnetic field. That means that whenever we plug the key, the magnetic field lines arise there around the secondary, first coil also, secondary coil also. And whenever we remove the key, there also there is change in magnetic field. Less number of magnetic field lines are there associated with the secondary coil. This is the reason for the induced electric current. So, the process by which a changing magnetic field in a conductor induces the current in another conductor is called electromagnetic induction, children. By this activity, we can understand this. In practice, we can induce current in a coil either by moving the coil in a magnetic field or by changing the magnetic field around it. It is convenient in most of the cases to move the coil in a magnetic field is more convenient. So that process is used in most of the places. Understood this activity, children? Through this we can understand about the electromagnetic induction. Here coil 1 is whenever current is flowing through coil 1, it acts as a magnet and magnetic field lines are varied by plugging the key or removing the key. So, by this process we can understand about the electromagnetic induction clearly. Children, now we know that a conductor moving in a magnetic field or changing the magnetic field around the conductor coil, we can produce the current that is known as induced current. Isn't it? We know about it. The moving conductor kept in the magnetic field produces current that is known as induced current. The induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. Observe, children, when the coil is moving in the magnetic field, current is produced. So, the induced current is found to be the highest when the direction of motion of the coil is at right angles to the magnetic field. That is, the motion of the conductor and the magnetic field must be at right angles to each other. Then we get the highest current, induced current. How we can know about the direction of the induced current then? For that, we can use a simple rule as we used in the motor. Which rule we studied before? That is Fleming's left hand rule, children. That is applicable to motor. So that rule is also known as motor rule. Which rule? Fleming's left hand rule is also known as a motor rule. But now, to know the induced current, the direction of the induced current, the magnetic field and the motion of the conductor, we use another simple rule that is known as a Fleming's right hand rule, children. How to explain this? Similar to that of the Fleming's left hand rule, but little changes are there. Stretch your right hand. Stretch your right hand and stretch the fingers of your right hand. That is forefinger, thumb and the middle finger at right angles to each other. Then the forefinger indicates the direction of the magnetic field. The thumb indicates the direction of the motion of the conductor. Then the middle finger indicates the direction of the induced current. Children, observe how to state Fleming's right hand rule and know about the directions. You can observe here. Here see children, this is a, like this if you hold, here you can observe, I wrote here magnetic field. This is the direction of the magnetic field. When we stretch our right hand, in this way also you can hold, in this way also you can hold, in this way also you can hold. But three fingers you have to consider. The three fingers, forefinger, the thumb and the middle finger of our right hand, such that they are perpendicular to each other. Then the forefinger indicates the direction of the magnetic field. The thumb indicates motion of the conductor. Then the middle finger indicates the direction of current induced in the conductor. Children, observe here. As I wrote here, you can use this rule. In this way also you can tell. But I wrote in this way here. Okay. So, how to state Fleming's right hand rule? When we stretch the forefinger, middle finger and the thumb of our right hand such that they are perpendicular to each other, then the forefinger indicates the direction of the magnetic field, the thumb indicates the direction of motion of the conductor, then the middle finger indicates the direction of the current induced in the conductor. So that is Fleming's right hand rule. Using this rule, we can find out the directions of induced current, magnetic field and motion of the conductor. This rule is also known as a generator rule. Why maybe it is called so? Because this principle is used in the generators which we are going to study in the next portion. Okay. So this is also known as Fleming's right hand rule is also known as the generator rule, and Fleming's left hand rule is known as a motor rule because it was used in motor. Children, now you are familiar about the phenomenon of electromagnetic induction. Am I right? The experiments what we studied to generate induced current in maybe in Faraday's experiments, whatever we studied that experiment to generate induced current, it produces very small current, children. Very small current is produced in those experiments. But the principle is very important. This principle is very important in the sense that it can give rise to the much amount of current also, if some changes are made and some devices are used. This principle, which principle? The electromagnetic induction is also employed to produce large currents for use in homes and industries. Always we are in need of large amount of currents, children. Small currents, it is not, it is negligible somewhat, isn't it? So we need large amount of currents for industries and homes also even. So which device can be used to produce the current, that is induced current? That is electric generator. That is which one? Electric generator, children. What is electric generator or simply generator? A generator is a device which converts mechanical energy into electricity or electrical energy. Generator is a device which converts mechanical energy into electrical energy. Here what happened, children? Mechanical energy is converted into which one? Mechanical energy converted into electrical energy. Whereas we came across the motor. The motor is a device which converts electrical energy into mechanical energy. Here vice versa, children. Here generator converts mechanical energy into electrical energy. Whenever we have load shedding or power cuts, we need generators, electric generators. In our schools also, whenever programs are going on in the middle, when power cuts are there, we use generators. Right? Isn't it? So, this is an important device. This is a big breakthrough in the field of, as I told you, a big breakthrough in the field of physics that is made by Faraday. That induced current, that is electromagnetic induction. That principle is now very, very important. Nowadays, we are having this much facilities regarding electricity because of that important principle. Now, the schematic representation of a generator is given here, children. I have drawn here. You can observe, children. Somewhat same as that of the motor, but little differences are there. Let me tell you later. Okay. Now, it consists of a rectangular coil as usual. We used in the motor also. Rectangular coil ABCD. You can observe, children, here ABCD is a rectangular coil. And this rectangular coil is kept in between two poles of a strong magnets. Strong, that is the magnetic field is there. In between that, the rectangular coil is kept between N and S. North pole and south pole, poles of a magnet. It is kept in between that. And here you can observe, children, R1 and R2. You can observe here, this is R1 and R2. R1 and R2 in blue colored, two circular structures are there. No, they are copper rings. Full copper rings. Observe, children, here R1 and R2 are full copper rings are there. Full one ring like or a bangle like, that is made of copper. Copper rings, two copper rings are taken, and there is the ends of these two. The ends of the rectangular coil are connected to R1 and R2. Internally, R1 and R2 are connected to an axle here. The light blue colored, you can see, this is an axle, children. This is an axle connected to that. They are insulated inside there. And you can observe in orange color, these two are B1 and B2. These two are carbon brushes. B1 and B2 are carbon brushes. They are pressed to the two rings. You can observe, children, B1 is near R1 and B2 is near R2. So, these two are carbon brushes to make the connection between outer circuit and inner circuit. These two are made of that is carbon, means allotropic form of carbon, that is graphite. As you know, graphite is a good conductor of electricity. So, here B1 and B2. Observe, children, these two are stationary brushes. You must know B1 and B2 are stationary brushes. Understood, no? And these brushes are connected to a galvanometer. Why do we use galvanometer? Galvanometer is used to measure the current or direction also. Direction of current also we can know from that. So galvanometer, here you can observe this is galvanometer, children. You can observe here this is a galvanometer, and R1 and R2 copper rings, full copper rings, and B1 and B2 carbon brushes, and ABCD is a rectangular coil, and N and S are the poles of a magnet, strong magnet poles. Okay, so in this way, how we can do now? The rectangular coil is rotated by that between the magnetic field. When it is rotated between the magnetic field, current is induced. That's what electromagnetic induction, children. Isn't it? We came across already. Yes. Children, now let us know how an electric generator works. An electric generator is a device which converts mechanical energy into electrical energy. An electric generator, as shown you can see here, consists of a rotating rectangular coil ABCD placed between the two poles of a permanent magnet. The two ends of this coil are connected to two rings R1 and R2. The inner side of these rings are made insulated. The two conducting stationary brushes B1 and B2 are kept pressed separately on the rings R1 and R2. You can observe their children respectively. The two rings R1 and R2 are internally attached to an axle. The axle may be mechanically rotated from outside to rotate the coil inside the magnetic field. You can see there it is rotated from outside. Outer ends of the two brushes are connected to the galvanometer. Here we are showing through a bulb. You can see there to show the flow of current in the given external circuit. We can use galvanometer also. Here in this case the bulb is used to know the presence of current. When the axle attached to the two rings is rotated such that the arm AB moves up and the arm CD moves down in the magnetic field produced by the permanent magnet. Now, by applying Fleming's right-hand rule, the induced currents are set up in these arms along the directions, observe children, AB and then CD. Along the two arms we are discussing, thus an induced current flows in the direction A, B, C, D. If there are larger number of turns in the coil, the current generated in each turn just adds up to give a large current through the coil. This means that the current in the external circuit flows from B2 to B1. After half a rotation, arm CD starts moving up and AB going down. As a result, the directions of the induced currents in both the arms change, giving rise to the net induced current in the direction DCBA. Observe children, in the reverse direction. The current in the external circuit now flows from B1 to B2. Observe children, brush B1 to B2. Thus, after every half rotation, the polarity of the current in the circuit or in the respective arms changes. Such a current which changes direction after equal intervals of time is called an alternating current, children. This is known as an alternating current, that is abbreviated as AC, alternating current. This device is called an AC generator. Whatever till now we discussed, that is an AC generator, because at every half rotation the current changes its polarity. Children, if you want to get direct current, whatever till now we discussed, we got AC, that is alternating current. If you want to get DC, that is direct current, what we have to do? With this arrangement, we cannot get a DC. which does not change its direction with the time. DC means what? It will not change its direction. So what we have to do? To do that, we need to use the split rings instead of the full copper rings. Here copper rings R1 and R2 were there, no? Instead of those rings, we have to use split rings. In the case of electric motor, we have discussed about that, isn't it? Electric motor, about split ring commutator we discussed. So that must be used to get DC, that is direct current, in case of generator also. So a unidirectional current is produced in the case of a DC generator, children. The generator of this type is called DC generator. Let us know more about what is the difference between AC and DC, children. The difference between the direct and alternating current is that the direct current always flows in one direction, whereas the alternating current reverses its direction periodically, every half a rotation maybe, like that. So what is the main difference between direct and alternating current? The direct current always flows in one direction, but alternating current flows in, that is, reverses its direction periodically. Children, most power stations constructed these days, they produce AC, that is alternating current. In India, the AC changes direction after every 1/100th of a second. After every 1/100th of a second, periodically it changes. That is, the frequency of AC is 50 Hertz. An important advantage of AC over DC is that electric power can be transmitted over long distances without much loss of energy, children. So AC is preferred over DC. Why it is so? The important advantage of AC is that electric power can be transmitted over a long distances without much loss of energy. So AC is preferred over DC. This is the reason for that. Understood, no? So this is about the generators through which we can get induced current. Have the knowledge of domestic electric circuits that were used in our houses. In our homes, children, we receive the supply of electric power through a main supply. It is also known as mains. It is taken from either supported through overhead electric poles or by underground cables. Isn't it, children? The power lines will be our overhead, or it may be underground cables also. We can have it. Isn't it? In our houses, we receive the AC electric power of 220 volts with 50 Hertz frequency. See, children, this is the schematic representation of domestic electric circuit. One of the wires in this is with the red insulation known as live wire, and another one with the black insulation, you can see there, is known as neutral wire. The potential difference between them is 220 volts. The third wire with green insulation is called as earth wire. This wire is connected to metallic body of the devices and deep buried inside the earth. It is used as a safety measure to ensure that any leakage of current through the metallic body of the device flows to the earth. The electric devices are connected in parallel always, children, in our houses, not in series. So earth wire protects our body from severe electric shock. And here you can see, after that these wires are there, no? Any wire may be live wire, neutral wire and the earth wire. These wires pass into an electric meter through main fuse, children. That is an important device. Fuse is an important safety device used for protecting the electric devices due to short circuiting or overloading of circuits. A fuse in a circuit prevents damage to the appliances and the circuit due to overloading. Here you can see, children, the different devices are connected in parallel. Always we should connect our devices in parallel, not in series. Okay, when these devices are connected in parallel, whatever the power required for different the devices, electric gadgets can be supplied. Otherwise, if you connect in series, what happens? If one device stops working, another one can't work. If one electric gadget is not working properly, then another also can't work, can't function. So that is the drawback of series connection. So all the devices in our houses are connected in parallel, so that if one gadget fails to work, then all other gadgets can work properly. Okay. Now let us come to fuse again. As I told you, it is a device which prevents damage to the appliances by overloading. When overloading can happen? Overloading can happen when the live wire and the neutral wire, they come in direct contact. Observe, children, here, when live wire and neutral wire, black insulation and red insulation, both of them, when they come into direct contact, overloading happens. This may occur when the insulation of wires is damaged or there is a fault in the appliance. In such a situation, the current in the circuit abruptly increases. This is called short circuiting. So, the fire may break out there because of short circuiting. So, the live wire and the neutral wire should not come into direct contact. When it happens so, it causes overloading and that causes short circuiting, from which the fire may break out in the circuits. The use of an electric fuse prevents the electric circuit and the appliance from a possible damage by stopping or the flow of unduly high electric current into the domestic circuit. Because of the Joule's law of heating in the fuse melts it to break the electric circuit. Understood, no, children? So fuse is very important device that must be used in our circuits, so that to safeguard our equipments, electric equipments. Overloading can also occur due to an accidental hike in the supply voltage. Sometimes what happens, the voltage may be higher. There may be hike in the voltage from the mains itself, from the supply itself. Then also overloading may happen. Sometimes overloading is caused by connecting too many appliances into a single socket. You might have seen to a single socket, many plugs are connected, many devices are connected. Too many appliances are connected to single socket. Children, what are the reasons of overloading? When the neutral wire comes in contact with the live wire, direct contact with the live wire. And another one is when too many appliances are connected to a single socket. And when there is hike in the supply voltage. These three reasons are there for overloading. Okay. Now, what are the safety measures we can follow? What are the safety measures used in the electric circuits, domestic electric circuits? First one is using fuse. Using a fuse. Secondly, earthing the circuit. Always it is a must to follow these two steps in our domestic circuits. using fuse. Check that in our house also, the domestic circuits also. Using fuse is a must, children. Fuse must be used so that we can safeguard the electrical equipments. And also secondly, earthing. Earthing prevents our body from electric shock. When there is any leakage of current to the metallic body of the appliance, if it is there, we may get electric shock. To prevent that, we can use earthing. What happens in earthing? If it ensures that any leakage of current to the metallic body of the appliance keeps its potential to that of the earth. So, these two safety measures we must follow in our domestic circuits.